Okay, the previous video got cut off just a little bit, so let me just explain one more thing, and that is that we did this was the wall for the t equals infinity condition, and the question can be, when is t equals infinity? And you can make an estimate of it using our consolidation type equation for the dimensionless time, or time factor, whatever you call capital T. And generally, as a rule of thumb, we can take, it's simple, it's not exact, but when capital T is approximately equal to 1, then we say that we have dissipated all of our U excess approximately. And so if we take capital T equal to 1 and solve for small t, which is the actual time, using C sub v and HDR, then we can make an estimate of what time t, small t, is t equals infinity. So in other words, I use capital T equals 1, tells me that, that is my sort of t equals infinity situation. Not exactly, but just this is all just, rough estimates. So by putting in capital T equals 1, solving for t, small t, and we get small t is equal to HDR squared over C sub v, and that is when we have U excess approximately equaling 0, and meaning t equals infinity. Well, what time is that? Well, we can look at our situation here, our soils, and what we're concerned about is dissipation of the pore pressure in this region. And how are those pore pressures going to dissipate? Well, there's only one place for them. They've got to go up. So this is basically a single drainage condition. It can't drain in both directions. It's got to go up in this particular case. And we have our H is approximately 6 feet, and that means HDR is approximately 6 feet, or the distance for water to travel to escape is about 6 feet, so that means that HDR is about 6 feet. So we simply use HDR of 6 feet squared divided by C sub v, and if we have a C sub v, for instance, of 2 square feet per year, then we have 6 squared over 2 feet squared per year. We get t is equal to 18 years. So we're looking at about 18 years is the time when all the excess pore pressures would be dissipated, and that's when we would consider the situation to be drained. Okay, so anyway, it's just a rough calculation if you're going to try to figure out when, in other words, when will these stresses be on our wall approximately, or when are we relying on those stresses to be on the wall? And that time is approximately 18 years after construction, approximately. And then I just want to re-emphasize these two equations here and the differences between them. Remember to memorize these. Hopefully you've already memorized the tangent squared 45 minus phi prime over 2, or in the passive case it's tangent squared 45 plus phi prime over 2. So this is our, this is our Ka and our Kp. So hopefully you know those. And then the coefficient over here is simply tangent 45 minus phi prime over 2, or tangent 45 plus phi prime over 2. So hopefully you know those two coefficients, and then all you need to do is, remember the minus 2c prime there, or the plus 2c prime there. And then we notice that in each case, whenever I have a negative there, I have a positive there. A negative there, positive there. Negative there, positive there. So for the passive situation, everything is plus. For the active situation, everything is minus. So, and like I say, these equations apply for t equals infinity in the clay. Okay, I want to note that now on the FE exam and the PE exam, the Fundamentals of Engineering and the Professional Engineering exams, you may not be given SU over sigma prime I. Sometimes they don't do that. Instead, they just give you an SU average over the layer. It's very common. So in other words, so let's just do a quick problem to show you how to handle that situation. So suppose I have this gravity wall here in clay, and I have an SU over the entire depth of 12 kilopascals, for instance, and you can see the dimensions here. It's 10 meters, 7 meters of the wall height. It's embedded 3 meters. So how do we handle that? Well, if you remember, okay, first we're finding the wall stresses at t equals 0 plus. So no, we're not doing the drained case. We're doing the undrained case because I want to learn how to handle this SU average. So if they give you an SU average on the exam and nothing else, then you know it's undrained. They're not going to. Sometimes they don't say that it's undrained. They're not going to say it's at t equals 0 plus. They're just going to give you these properties and say what are the stresses on the wall. You have to infer that it's undrained. So we've already developed that the maximum unsupported depth is 2 SU over gamma saturated. So we're going to use that. So we're going to start with determining what that unsupported depth is. And in this particular case, since our SU is 12, I put in the 12 there, and then gamma saturated is given to be 20. So 2 times 12 over 20 is 1.2 meters. Well, what does that mean? That means that for the first 1.2 meters, so when that distance is 1.2 meters, there's really no stress on that portion of the wall because that is the maximum unsupported height. And so when I plot up my stresses, this distance of 1.2 meters, I have no stress in that region. We're not going to put down negative stresses or anything like that because they don't really exist. Usually there's some sort of separation or cracking or something like that, and we don't want to take into account negative stresses in this particular situation. So we start there and determine downward from there what the active stresses are. So when we fill out our table, and remember we just need 3 columns because for the undrained case it's much simpler than the drained case. We start at 1.2 and then we have 10. So, and then my sigma v, we all know how to get that. 1.2 times 20, 10 times 20. And then we simply go straight from sigma v to sigma h, using our, in the active case, sigma v minus 2su. So of course, you can figure this out because of the way that it works out. This is going to be 0 because, in a sense, that's how we got that number. So this is, if we do everything right, that will always end up to be 0. And then we figure out that one. It's the 200 minus our SU is 12, so 2 times 12 is 24. So 200 minus 24 is 176. So I get 0 and 176 there. There's my active stress. My passive, so now I'm looking on this side for my passive. My sigma v is going to be 0 and 60 at the base, just 3 times 20. And for the passive, I'm going to have what? I'm going to have sigma v plus 2su. So I simply take that sigma v plus 2 times 12 is 24. And this is going to be 60 plus 2 times 12 is 84. So here are my passive, there is my active. Obviously this wall is not likely to be stable, but this is how this would be. This is how you would calculate the active and passive pressures. Of course, it depends on how big that wall is. Probably need a pretty big wall there to make this one work, because you can see that the passive is so much lower than the active. Okay. All right, so one thing that we haven't gone into detail is for sliding, what is the resistance at the base of the wall? So let's talk about that in a little bit more detail especially for the clay undrained situation. So what we're going to do for the time being is I'm going to illustrate what's at the bottom of this wall. We're going to assume a very rough wall at the bottom. So in other words, if I blow that up, in other words, make a bigger picture of that, if I have a very rough wall, what does that look like? Well, I'm showing a very jagged edge here. If I have a very jagged edge, which means very rough, then what's going to happen, I'm going to have, clay in these little voids between the jags, and I'm going to have clay down below. So then I have my clay also down below. So you can see that when this moves in this direction, when the wall moves in that direction, when it slides, what's happening? I'm getting a shear plane, clay on top, clay on the bottom, except for these little peaks in the concrete. So it's a clay to clay shear surface. And so we can take our tau FF on that shear surface as being SU. So the undrained, it's because I'm shearing the clay right there. It's like a little miniature direct shear test on the clay. So my shearing resistance is simply going to be SU, because it's like a direct shear test when this wall moves in that direction. So that gives me the stress at the base of the wall. I need to convert that stress to a force. Well, what do I know? Stress times area is force when the stress is constant. So we're going to multiply by the area of the shear surface. I'm going to take 1 unit in length perpendicular to the paper or to the screen. So my force at the base, shear force at the base, is going to be SU times the width B times 1 perpendicular to the screen. And remember that our failure envelope for clay undrained looks like that, so we have to always remember that. So when I draw my free body diagram at the base of the wall, okay, it's going to look like that. In other words, my force is going to be my SU times B times 1. I also have a normal there. I'm primarily, for sliding, I'm interested in the resistance, though. So the shearing resistance. So it's going to be SU times B times 1. And, okay, so that's how I handle the situation for clay undrained, T equals 0 plus. For sand drained, then, how do I handle that situation? In other words, what I had before was I had clay next to the wall, clay below the wall. Now suppose, I guess I'm showing clay here, but I have sand underneath. I'm really wondering because now it's sand that is shearing here. And And again, for the sake of discussion temporarily, we're going to take that we have a very rough wall again, but this time it's going into the sand. In other words, down below, this is, we're going to have sand here. So how do we look at it in that case? Well, again, when I do my free body diagram, I'm going to have a normal and a shear when I make my cut underneath my wall. And the normal will be a sigma prime, and the shear will be a tau. It'll come from our failure envelope here, where this is sigma prime, and that is my tau FF. And what do I know? I know that tau FF is what? Sigma prime tangent phi prime, which we've done already. Which means that what, as we said before, tangent phi prime is like our coefficient of friction. So when I do this, I'm going to have, again, I have to, because this is all sigma prime, not sigma, it's sigma prime. So remember, I have to separate the water and the water pressure from the contact force. And so what we're going to do is we have the vertical equilibrium of this wall. For instance, I've got the weight of the wall, and so this wall's got to be in equilibrium. So I'm going to have vertical forces going upward that are equal to the weight of the wall. Well, I'm going to break those vertical forces into a pore pressure force and call it an effective stress force. So we call it an N prime and U. And we know what U is. U is going to be the pore pressure at the base, U, small u, times the area of the base. That's going to be my water pressure force, pore pressure force. So I know what the U is. I know what the weight of the wall is. And then N prime is simply going to be the weight of the wall minus the U. So my friction, using old notation in a sense, or your notation from your statics class, it's mu times n prime, a mu n type term, and because mu is tangent phi prime, we have that the F is n prime tangent phi prime. And that gives us so this is our friction force for sand drained. This is our friction force for clay undrained. When we have clay drained, now what do I have to do? Again, I have to separate out my pore pressure at the base and my effective stress force at the base. And we do the same thing. I get that N prime is the W minus the U. We know the U. We just did it previously. But now we have to recognize that our failure envelope now is different. Our failure envelope now has an intercept of C prime. And that means that our tau FF now is going to be, well, again, we can do this little triangle. This portion right there is going to be, as we had before, sigma prime tangent of phi prime. And then we have this is C prime. So we get that our tau FF, as you can see from just using geometry, is going to be the C prime plus sigma prime tangent phi prime. So that gives me my tau FF, and then I sort of have the combination of the two that I just previously did, which is I'm going to have the we're going to have the C prime times B times 1. As you can see, that's what? That's similar to the SU times B. Except that, we're substituting C prime because now our intercept is called SU, or intercept is called SU here, not C prime. So I have that term, whoops, and I have that term. So I have both of these terms. So I've got, this one's going to be C prime times B, and this is going to be the same. So I have the effect of both of these, because in a way, my clay drained is sort of, failure envelope is a little bit like the sum of those two. So the end result is that I have my friction force is going to be C prime times B plus N prime tangent phi prime. So I know this page, so you know what your friction forces are. So you need to know this page, both of these pages. So I got, again, so for clay undrained, there's my friction force. For sand drained, there's my friction force. And then it's easy to get clay drained because we just add those two in a sense, and we get clay drained. Although we have to substitute, we have to put C prime for that, for the clay drain situation. So that's how you can remember it. Now, what does that mean in terms of when we evaluate a wall? So if I look at this wall built by excavation, okay? So it'll be find the stresses at T equals infinity and the base force. So, okay, so we're looking at the T equals infinity situation. The wall is built by excavation, which means that my T equals 0 plus situation has sand here. My T equals 0 minus situation has sand on both sides here. My T equals 0 plus situation excavates all of this. So that is removed. And all the soil properties are given here. And so I have my sand. Well, sand has a C prime of 0, phi prime. Does not have an SU over sigma prime I. My clay has a C prime and a phi prime and an SU over sigma prime I. Now, in this particular case, we are asked for everything at T equals infinity, so I'm not really going to need that because that's an undrained property. So, okay, so what do we need to do? Since we're doing T equals infinity, we're going to do an effective stress analysis because it's what? It's EDS, effective, drained, slow, because it's at T equals infinity. So I use effective stress analysis, meaning that I have to fill in all the columns of my table. And so we've done this many times, but notice the water table is right there. And so I'm going to assume, well, we have our depths here. We have our depths of 2, 6 minus, 6 plus, 12, 6 and 12. Oops. And okay, so let me just well, you can do the sand, And there may be a little bit of a mistake here, but let me just double check here. Oops, I didn't go through it all. Okay. Okay, I must have made a little mistake. That should really be 0 there, but I'm not going to go through and change it right at the moment. So I must have made some sort of change to this problem. But no matter. Let's just go through the stresses. You can all do the sand, so I'm not going to go through that again. We've done that enough times. We had our... Oh, well, let me just make the following comment. We need to get the... for the sand, I need to get my Ka. And Ka, of course, is tangent squared 45 minus phi prime over 2. I plug in the 33. I get a Ka of 0.238. So I use the 0.238 in the calculation of sigma h prime. And for the clay, you can all get the sigma v's. I'm not going to go through that. You can get the u's. I'm not going to go through that. That means you can get the sigma v primes. It's the sigma h primes that we're going to focus on. So when I'm in the active region, then I use the active equation. And here's that active equation applied to there. And, we plug in the sigma v prime and we can get those two numbers. In the passive region, again, you can get all the sigma vu and sigma v primes. How do I get the sigma h prime? Well, now I apply the passive equation, which is the same thing, only with plus signs. And I plug in those values. I get that little simplified equation, and then I'm going to get those two numbers for the sigma h primes. And then I add in the pore pressure, and I get these. Okay, so that gives me, these are the active stresses, these are the passive stresses. Now, what is the U at the base of the wall? That is what we just sort of covered. The U at the base of the wall. How do I get it? Well, we're talking at t equals infinity. That means what? That means I'm going to have I'm going to use my C prime and phi prime, and that means I have to use the expression we developed last time, which is C prime B plus N prime tangent phi prime. So I use that expression. The first thing I have to do is get my N prime. So how do I get that? Well, I get the water pressure force at the base. Well, where does that come from? Well, I know what the water pressure is. It's 374 is small u at the base of the wall, and I take it times the width of the wall b times 1 perpendicular to the screen or the paper. The b is 3 feet, so I have the 374 times 3 feet times 1 gives me 1122 pounds. That gives me the upward water pressure force. The weight of the wall, it's 3 feet wide by 12 feet deep, 150 pounds per cubic foot for the unit weight of concrete, 1 foot perpendicular to this paper. I get 5,400 pounds, so the difference between those two, 5,400 minus 1122, that is my N prime, so that's going to give me 4278. That is what is available to help produce the friction. So that is going to give me, there's my equation that we developed on the previous page, or 2 pages ago. And I simply put in my C prime of 100, B is 3, times 1, N prime, that is that value right there. and then tangent of phi prime is 20 degrees. So I get my friction, where we get our resisting force, our sliding resisting force of 1857 pounds. So that's how we get the sliding resistance, the base for this situation. Let's see, well, okay, so the weight. All right, this doesn't pertain to this particular problem here, so I'm going to skip that. All right. I want to make a couple other points here, and I'll just note the following, that one of the things that we'll say miscellaneous geotechnical issues. Suppose I have the situation where I have a fine sand here, and it can be possible that I have a water table level that is not the same on both sides of the wall. And if that happens, then what's occurring? Well, I'm getting flow around this, underneath the wall, as we've observed before. And so what do? You make a flow net, if you remember how to do those. And with that flow net, then we can determine the water pressure at the base of the wall, for instance. We can also get the water pressure on the side of the wall, but so you have to sort of refresh your memory on how to use a flow net. But as an approximation, we can get, well, I can look at these pore pressures there, and as an approximation, I can do this. It's in some cases, it's a good enough rule of thumb. It's the water pressures are less than this, but this is a little bit conservative. So, in other words, if I simply ignore this effect taking place and I want to be conservative, I can say that I can get 10 feet of water pressure on this side and 4 feet of water pressure on this side. And that would give me basically 10 feet times 62.4 there, 4 feet times 62.4 there, and I can make a little trapezoid of it. And that'll give me an approximation. A rough draft, for this class we can do that instead of making you draw a flow net for this case. So you can just use this as a rough estimate of what the pore pressures are at the base, when I have a water table that is different from on both sides of the wall. And as I said, you can get from the flow net, this is a little bit of a review, you can get the pore pressures along the side of the wall. So, in other words, this is a little bit messy, so I apologize for that, but when we're doing our table of sigma v u, sigma v prime, sigma h prime, sigma h, well, what goes in the u category? So, in other words, what goes there? Well, what goes there comes from the flow net. And how can we get it? Well, this takes you back a little bit, but how do we do these problems? And this is a little bit messy, but let me give it a try. What do? We count the number of squares for one flow path. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9. I have 9 squares in one flow path. That means that each square I drop 1/9 of the total drop. So the total drop here is 4 meters. That's my total drop because my water table is there, my water table is there, a drop of 4 meters. So each square in the flow net drops 1/9 of 4 meters. So 1/9 of 4 meters is 0.44 meters. So when I draw my little piezometer, if you remember how to do that from that point, well, I drop the drop. So the drop is the change in the water level. So in other words, the water level drop that shows in the piezometer is 1/9 of 4 meters. So it's 0.444 meters. And when I go to here, it's going to be 2/9. So this drop here, whoops, that drop there would be 2/9 times 4. So that gives me, well, 0.888. So, and then to here, I don't show a piezometer, but that would be 3/9. And then the one that I do show is right at the bottom. Well, that's 3.5 ninths because it's 3.5 squares I've gone. And 3.5 times 4 is 1.55 meters. So I can figure out using geometry. I don't want to review flow nets all the way at this particular time, but once I know the drop, then what? The pore pressure is this distance. So I use simple geometry to figure out that distance, for instance, which is going to give me the U at the base of the wall. And then I also would get, you got to use the picture. I get that. That is going to give me the U there. That distance times 9.8 kilonewtons per cubic meter. And then, this distance here would give me that value when I multiply it times 9.8. So you got to look at the picture, do some scaling and things like that. And that's all about getting this U number. And then I have to repeat that exercise on the other side of the wall to get those numbers. So that is how you do it when you have a water table that is different on both sides of the wall. You can take a look at, there's the calculations, and you can review your flow nets a little bit to get those details of what those pore pressures are. So you can pause the video, look at those calculations. And you may have to revisit your flow net calculations and go back to Engineering 430. You can look at some of those YouTube videos and they will describe flow nets in more detail if you don't remember. Okay, let me just see here. All right, I'm gonna stop there.